Hello and welcome to another episode on this channel. Today we look at the Monty Hall Problem. The Monty Hall Problem, you are required to pick a door. If you pick the correct door, you get rewarded with a car. But if you choose the wrong door, you end up with a goat. So there's a car door and then there are two goat doors. The way this problem works is you're at a game show, and the game show host allows you to pick the first door right away. So once you make your first initial pick, the game show host goes on to reveal one of the GOAT doors. And in doing so, he leaves you with the choice to either stick with your original decision, which in this case is the first door that you chose, or switch to the other unopened door, which then happens to be door number 3. Okay, so in terms of probability, in terms of actual numbers, what are your chances of winning if you stay with your original pick or if you switch to the other unopened door? That is the question that we want to answer in today's video. So the way I would want to do this is illustrate by showing each and every possible scenario and come to a numerical value of probability of winning. So let's start with the first possible scenario. Say, and we could assume that the car door is always door number 1, and then we could go over different possible scenarios while fixing the car door as door number 1. So let's look at the first scenario. So like I said, car door is door number 1, and you have 3 options to choose from: door 1, door 2, or door 3. If the car is behind door 1, door 2 and 3 would have goats behind them. Alright, so you make the first pick of door 1, and that is the correct pick, but obviously that door does not get revealed. So Monty, the game show host, he has the option now to reveal a goat door. Now he has 2 options. He could either reveal door 2 or door 3, since both of them have goats behind them. So if we follow this branch, the branch above, and try to understand that first, let's say he opens door 2 to reveal a goat. What that means is now you have an option to choose between door 1, your original choice, or door 3, because he opened door 2. So you could either stick with door 1 or you could choose door 3 in this first case. Now if you stick with door 1, you win because that's the car door. But with the door 2 opened, if you switch from door 1 to door 3, you end up with a goat. So you lose. Now let's look at the other branch, which is fairly similar, is because he opens door 3 to reveal a goat, leaving you with the choice to pick from door 1 and door 2. And if you stay, you win, but if you switch to door 2, you lose. So to summarize this first case, where you first pick where your first pick is the first door, it does not matter which door Monty opens. If you stick with your original decision because your original decision was correct, you end up winning. But if you switch to either of these doors, you lose. Okay, now let's move to the second scenario where you initially pick a wrong door, door 2, and then Monty does not have an option to open. Really, he has only got door 3 to open because you pick door 2. He cannot open door 1 and reveal the car and end the game right away. So he only has door 3 to open and reveal the goat. Remember, he only reveals a goat door at this stage. So once he reveals a goat behind door 3, you've got an option to either stick with your original door 2 or switch to door 1. In this case, if you switch, you win. If you stay with your original pick, you lose because you originally chose the goat door. And the third case is similar to the second case because you pick a bad goat door, the wrong choice initially, and he has to reveal a goat door, and the goat door is door 2, cannot reveal your pick. He cannot reveal the car door, so he reveals the goat door in door 2. What that means is you either stay with your original decision or you switch. If you stay with your original decision, you lose. You switch, you win. Now, once we have finalized these possible scenarios that are there, let us now look, before we head down to the probabilities associated with these picks, let us first try to make sense intuitively out of this. Now, right away, there's one pattern that is evident, is that since there's only one winning door, one car door, there are higher chances for you to make a bad pick initially. There are 2 bad options and 1 good option, 2 wrong options, 1 correct option. So it's more likely for you to pick a wrong option initially. And what that means is, if you are picking a wrong option initially, at any stage of the game, if you're given an option to switch, it would make more sense for you to win by choosing to switch, because there's more likelihood of you picking the wrong doors initially. Therefore, intuitively at least, it makes sense to switch at any point in the game. Well, that's just an intuitive reasoning out of this. Let's look at the probabilistic numbers and see if that matches up to our intuitive understanding. So 1 by 3 probability for your initial pick is fairly easy to understand, because you've got 3 options and you pick each option by a probability of 1 by 3. Your probability cannot be influenced in any way, so that is fairly straightforward. Now, once you make your initial pick, what is the probability of host opening either of these doors? It's equally probable, because they're both goat doors. So there are 2 possible options. For door 2 to open, it's 1 by 2 is a probability. For door 3 to open, 1 by 2 is a probability. Let's look at this 1 by 1 and 1 by 1 here. Why do we say the probability of door 3 being opened in this second branch is 1, or 1 by 1? And that's because there are really no other options for the host to open any other door, because he cannot open your pick door 2, he cannot open door 1, because door 1 was the car door, so he's only left with 1 goat door to open, and that goat door is door 3. So the probability is 1, it's absolute 1 for this door to open, and same is the case with the third branch also. And as is the case with probability tree diagrams, you multiply along the branches. So that is how you arrive at 1 by 6 for this upper branch and 1 by 6 for this lower branch in the first case, 1 by 3 in this second case, 2 by 6 is 1 by 3, and then 1 by 3 or 2 by 6 in the third case as well. For this, obviously, for the first scenario where there are parallel branches, you add the resulting probabilities to arrive at the final answer, which in this case is 2 by 6. So if you stay with your original decision, the probability of winning as a whole is 2 by 6. The probability of losing as a whole is 4 by 6. So staying with your original decision means your probability of winning is 1 by 3 or 2 by 6. It's lower as compared to the probability of losing. So there are more chances that you would lose if you stay with your original decision. Now the other side of this is, because we listed out the cases, so we could easily see that if you switch, obviously if you win and if you lose, the probabilities remain the same, but it's just a different way of saying that if you switch, your probability of losing is 2 by 6, whereas your probability of winning is 4 out of 6. So it makes sense for you to switch and have a higher probability of winning. Notice that these are the same. It's the same thing. It's just a different way of saying it, whether you stay or whether you switch. But the probabilities remain the same. It makes more sense to say it out like this, that switching has a higher probability, or to say that staying with your original decision has a lower probability. It's the same thing. But now we've seen that in terms of numbers and in terms of intuitive sense, it makes sense for you to switch in a game show where your probability of winning depends on your switching in probabilistic terms, and that is down to the fact that there are more chances for you as in this case there were two possible chances for you to make a bad decision originally. So it's better, you're better off switching or changing your decision. I hope that makes sense, and I'd be happy to answer any questions in the comment section. Thank you so much.